Hello, picking back up where we left off in the last video, we factored out the tan of delta x, and we got the 1 plus tan squared left in here, and we had the same denominator down here. Now, remember from trigonometry, 1 plus tan squared is secant squared, so here's that, and I left the denominator b for the time being, or just for this step anyway. Now here's the thing, guys, this secant squared of x, it just has x in it, not delta x, so we can take it out to the side here. Because relative to delta x, secant squared is constant. And again, that's relative to delta x. So we get this limit right here, times the secant squared, that is. And then times again, this is, if they don't write a symbol, it's understood to be multiplication. So times again, the other limit, the product of the limit is the limit of the products of this guy right here. And, well, as long as you don't have infinity times 0 or anything like that, but that's not going to happen. So we have this, we break it up. Now, tan, remember, this limit is 1, because the tan can be thought of as sine over cosine, but you can throw 0 into the cosine directly, and cosine of 0 is 1. So this limit is 1. And you get secant squared times 1 times, and by continuity you can throw delta x into here, but the tan of 0 is 0, but don't be scared, you still have a 1 down here. 1 minus 0 is 1. So you just have 1 over 1, which is another 1. So you just have secant squared times 1, which is secant squared. Okay, after all that stuff, after all of those steps, some hard ones at that, we have shown that the derivative of the tan of x is the secant squared of x. And I'm trying to scroll back up to get to my original. So sure enough, for any point at which the tan is defined in this particular subset of the reals right here, at any point where the tan is defined, the derivative of the tan is the secant squared. That's pretty cool. Okay, so that's all for that. So I don't want to do this forever. We're just pushing limits, and I'm showing that we can do it with trig functions and all that. And I wanted to do rational functions and roots, and I think we've pretty much done that. Now, if you have something like the cube root, remember that's x to the 1/3 power. And then by definition, the derivative is the cube root of this, x plus delta x, minus the cube root of x over delta x. That's just the limit of the difference quotient. And then, so that's the limit of, now, here's what you got to do. This is going to be a little strange. That's the limit as delta x goes to 0. Now, you can think of this as a, and you can think of this as b. So the cube root of x plus delta x, in your mind, let that be capital A. And the cube root of x, let that be capital B. So we got capital A right here, minus capital B right here, times the following: a squared plus ba, but the cube root of x times the cube root of x plus delta x, you can, since you can bring that all inside, and that's the cube root of x times parentheses x plus delta x. So this is the cube root of b times a, where we use the bring-in law, like the cube root of p times the cube root of q is the cube root of quantity pq. So here's a squared plus ab plus b squared. And again, the square of the cube root of x is the cube root of x squared. They're the same thing. You have that liberty. And likewise here, the square of the cube root of x plus delta x is the cube root of parentheses x plus delta x squared. So we have some liberty there. Okay, by algebra. Now, you're like, again, guys, what I'm doing is a minus b, I'm pairing that up with a squared plus ab plus b squared. And what that's going to do, if I multiply that out, remember, that's going to give me a cubed minus b cubed by the difference of cubes. Now down here is just the price I've got to pay. Since I've inserted this guy up here, I've got to insert this guy down here, the same guy. It goes down here with my delta x. Okay. Now, here's the thing. You're like, well, Jason, why do you want a cubed minus b cubed? Here it is. Here's a cubed minus b cubed. But that's a pretty thing to have, because the cube of the cube root is just the guy himself. So the cube of the cube root of quantity x plus delta x is quantity x plus delta x itself. And the cube of the cube root of x is just x himself, on the other end of the minus sign right here, okay? Well, but hey, lo and behold, the x and minus x kill each other, and you're just left with delta x over this. So that's always nice. But hey, that's valuable. The cancellation of these x's means a lot, because then you can cancel this delta x division-wise with this delta x down here. We cancel the x's subtraction-wise. We cancel the delta x's division-wise, which gives us understood 1 up top. So this delta x kills this delta x, leaving a 1 up here, the multiplicative identity. And then this guy, you can take the brackets off, because that delta x that was binding them is gone. So you just have 1 over this guy plus this guy plus this guy. And, well, but hey, by continuity, you can throw 0 into delta x, and you just get 1 over the cube root of x squared plus the same term again, plus the same term again. But that's just 1 over 3 times that guy. So that's just 1 over 3 times. Now, this can be written as x to the 2/3 power. You put the 2 on the numerator and the 3 on the denominator. It's always that way in any, as long as the domain's appropriate. The cube root of x squared is x to the 2/3 power. For example, if this was a 7 out here and a 4 in here, we would have x to the 4/7. But anyway, since it's a 3 out here and a 2 here, we have x to the 2/3. The index goes on the denominator, the power 2 goes on the numerator. Okay. But then that's 1/3 x to the negative 2/3. Remember, a negative exponent means reciprocal. Okay. And that's all for that. And in this next example, I do a hard one just to bring it on home. You probably won't, I can't swear to it, but you might not have to deal with this in a real college course. But depending on the taste of your professor, I don't know. But this is kind of steep. What if you have a general nth root, and let's just say you keep it domain appropriate? So you're positive if we take the even root. You're non-zero if we take the odd root. So, and let's see here. And like up here, back when I did the cube root, I should have been more careful about something. We don't want 0, because even though the function is defined at 0, the derivative would go to infinity. So that's the only mistake I made. I should have left 0 out of the domain. Sorry about that. So I'll save that, here in a minute. But anyway, and so here we just don't 0 in the domain. If it's odd root, if it's even root, it's more strict. You got to be positive. So we're doing the nth root of x. And then you just do dy by x equals this guy minus this guy. But then by the rules of algebra, what you do is you do a minus b, let this guy right here be a, and then separately let this guy right here be our big B, capital B. So this is a minus b. Now this is a to the n minus 1 plus a to the n minus 2 times b. And I went ahead, that x right there, I went ahead and brought it in. Because what we're doing here is we're doing the nth root of x times the nth root of parentheses x plus delta x to the n minus 2. But we can bring that nth root of x, we can bring them together like this. So so what we got is we got a to the n minus 1 plus a to the n minus 2b, and then plus a to the n minus 3b squared. And then if I kept going, it would be a to the n minus 4b cubed, a plus a to the n minus 5 b to the 4th, plus a to the n minus 6 b to the 5th, plus blah, 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 all the way, but it won't go forever. Plus, notice that a is decreasing and n is not infinite. It's just an integer. Of course it's not infinite. Plus, we'd actually get down to a squared b to the n minus 3 plus a b to the n minus 2 plus finally b to the n minus 1, which is this guy right here. What's going on here? Notice that a to the n minus 1, the power is n minus 1 right here. And notice here we got a to the n minus 2 power times b to the 1 power. Well, if we can't really add the exponents because we got two different bases, but in our heart of hearts, if we could add the exponents, n minus 2 for the a term plus 1 for the b term would give you n minus 1 overall. The sum of the exponents will equal n minus 1, even though you can't really multiply different bases like that, you know. And like here, we got b squared, a to the n minus 3, but n minus 3 plus 2 is n minus 1. And let that be your guide. And then here at the very end, we go, you know, our a is gone and we got b to the n minus 1. And then we had to put the same thing down here to consolidate. And then we just follow the bread trail of what we did with the cube root, sort of, kind of. And now, guys, here's the thing. Remember, by the rules of algebra, this guy right here is going to be the nth root of a. No. It's going to be a to the n minus b to the n. Remember, this is a and this is n, just plain Jane n, the nth roots, or the a and the b. The nth roots of the things to the n powers, that's a to the n right there, minus b to the n. So by the rules of algebra, this product here is a to the n minus b to the n, which is this nth root of right here, minus this is nth root right here. But there's a difference. Notice there's n powers in there now. We're raising a to the n power. We're raising b to the n power also. So this is a to the n minus b to the n. By the rules of algebra, a minus b times parentheses b to the n minus 1 plus a times b, or no, excuse me, a to the n minus 1 plus a to the n minus 2b plus a to the n minus 3b squared plus yada 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 all the way down to b to the n minus 1 equals a to the n minus b to the n. Whew. Now you're like, well, Jason, why did you go through this trouble? Why did you do this right here? What was it worth it? Yes, it's going to be. Because remember, guys, you see that n and that n, we can write this as parentheses x plus delta x to the n over n power, but n over n is just 1. In other words, remember the n, or to say the same thing, the nth root of the n power self-destruct. And you're just left with plain Jane x plus delta x. And likewise here, on the other end of the minus sign, the nth root of x to the n is just x. So you're just left with plain Jane x. Bye-bye. The x minus x are going to cancel. You're just left with delta x here. So these cancel subtraction-wise. And then these delta x's here and here will now cancel division-wise on the next step that we're going to do. And they leave in a 1 right here. Okay, right here. And then we just get 1 over this guy. But then by continuity, you can throw 0 into delta x, and you just get the nth root of this guy to the n minus 1 plus the nth root of the same guy. And it's going to be to the n minus 1, guys, because x times x to the n minus 2, you get just this, but this is 0 now. And after we throw 0 into delta x, so x to the n minus 2 times x to the 1 is x to the n minus 1 by the law of exponents. You add the exponents. And then here you get another nth root of, well, x to the n minus 1. For you add the 2 to the n minus 3. And then so on. And another. Now, how many of these have we got? We got to count our tallies. These are all nth roots of x to the n minus 1. We got 1 here. Well, really, if we count our x's, like here we got x squared, x cubed all the way to n minus 1. So you'd be tempted to think we got n minus 1 terms, but don't forget to add the original first guy that didn't have any x's, that didn't have any plain x's without delta x on it. So you have this original guy here, so you can think of this as the 0th term. Then x to the 1 is the first term, x squared is the second term, x cubed is the third term, and then this would be the n minus 1 term. But don't forget we had a 0th term, so we really got n terms, not just n minus 1 terms, but we got n terms because we had a 0th term right here. So we got 1, 2, 3, 4 n terms down here of the same guy. So that's we add the nth root of x to the n minus 1 to himself n times. So that's going to be n times the nth root of x to the n minus 1. Let's go down here. Here I show it off. So again, I throw my zeros in, but these are all the same guy. See, I show all the steps. Sorry for talking too much without showing this. I should have showed this a minute or two ago. But here's all this. Again, I just kill off my delta x's. 0 is just dead. X plus 0 is just x itself. And, well, if it'll scroll down for me, I had to go to the next page. But again, here's what I was talking about. Here are those nth root of x to the n minus 1s that I was talking about. But that's one, we got n of these, right? So there's n of these. So it's 1 over n times the nth root of x to the n minus 1. Now you can stop here. Your professor, she or he may be satisfied. But if they want it, if he or she wants it in exponent form, you would put the n minus 1. Now, technically, it would be 1 over n times x to the... It would be 1 over n. And if you left the x down here with the n, it would be x to the n minus 1 over n. But I did reciprocity and I negated. I turned n minus 1 into 1 minus n because the negation of n minus 1 is 1 minus n. And I wanted to bring x is now understood to be up here with the numerator. So this is n minus 1 over n down here, but then when I bring it up, I stick a negative on. I distribute that negative through the n minus 1, and I get 1 minus n. Whew. So, but that's going to be 1 over n, and then you can break that off as x to the 1 over n minus 1. So you can write it like this if you want to. And what the reason I wrote it like this is I'm going to amplify later. You bring the original exponent down, and you subtract 1 off of off 1 over n. You said, like, if this is x to the 1/3, it would now be 1/3 x to the 1/3 minus 1, so it'd be 1/3 x to the 2/3. No, excuse me, it would be 1/3 x to the negative 2/3. My bad. So it'd be 1/3 x to the negative 2/3. And that should be what I got on that last example. It better be what I got, or it means I've done something amiss. Yep, there it is, 1/3 x to the negative 2/3. And again, it's not positive 2/3 up there, it's negative 2/3. So a minute ago I should have said negative 2/3, not positive 2/3 up here. But anyway, there's that, because 1/3 minus 1 is negative 2/3. Okay, so there's that. Let's see. Whoa, what a rush. Okay. But anyway, that's that for that. And then I do the fourth root just to show it off. So, like, just to show it off, here's the fourth root, and here's a minus b. Now, since 4 is your root, you're going to do a cubed plus a squared b plus ab squared plus b cubed. And then by the rules of algebra, that's a to the fourth minus b to the fourth. But then the fourth root of the fourth power, they kill each other, and you just get this. And the x minus x is 0, so that's just going to leave delta x by himself. But then he's vulnerable, so divide delta x by delta x, and you get 1. And then we claim that all 4 of these terms down here are the same guy, because, you know what, we're going to make delta x 0, and we just get the fourth root of x cubed every time. And as we can see if we scroll down, yep. Notice x times x squared is x cubed. Wink, wink. So there's that. So we just get the same old guy, added himself 4 times. So that's 1 over 4 times the fourth root of, well, it's x cubed. Yeah. So x to the 4 minus 1. Now, I kind of, it's okay. If you want to just, this is x cubed, but I decided to be coy and write that as 4 minus 1 instead of 3 up there, just to illustrate that this is going to be 1/4 x to the 1 minus 4 over 4. And then I break that off like that. You can fragment the fraction like that. And so that's going to be 1/4 x to the negative 3/4. You can not bother. You can just write this as, you can put a 3 right here, and that's going to put a negative 3 right here, and you can be done with it all. So maybe I was a little too coy for my own good. I didn't say anything wrong. I just don't know if I was as efficient as I should have been. But this is fine if you want to do it this way. I'm out of time. Thank you guys. I'll see you on the next video.